Alright, hi everybody, welcome back to our C++ programming course. This is our fourth lecture now, and let's have a look what we are going to discuss about today. So today we are going to discuss about unions, so maybe more general, not only about unions, enumerations and all that good stuff which I listed here, but in general today's lecture are going to be mostly about user-defined types. So how can you as a user define your own data types to be used for modeling a piece of software, a larger program that solves a particular task. And so you can actually define multiple user-defined types. So we have some kind of union types, we have enumeration types, which I listed all here. And we are also going to discuss about how to define user-defined types using structs and classes. So all about user-defined types. And at the very end, we are also now discussing today how to organize C++ projects. So at some point, probably not in this lecture, but maybe later on in your career, or if you in your master thesis maybe have to implement a larger piece of software, larger project, then it's very important on how to organize C++ projects, and we will discuss about that in today's lecture. Also, if you then eventually have some larger projects, how do you manage them? How to check for a unified look and feel of your programs, and you can of course use automated tooling for that. So luckily nowadays we have automated tooling which help you to organize and structure your C++ projects, and also C projects. So that would also apply for C as well. So we are going to discuss that at last in today's lecture. All right, note on this lecture. So, I mean, last time we discussed about pointers, which are somewhat tricky. I mean, for now we only really saw the easy parts. Today's lecture we will also discuss about a harder topic, user-defined types and special member functions. We also have to discuss in that context. And it gets somewhat worse in next lecture. In the next lecture, where we also discuss about dynamic memory allocation. And so mostly you use all those three things together. So meaning pointers and references, user-defined types, and dynamic memory allocation. You mix it all up to get the most out of it. But that also is probably why today's and next lecture are going to be a bit harder. So that's usually developers at the beginning of a project. So yeah, I'm ready to do it. And at the very end of a project, it's kind of madness evolving. Hopefully that's not you at the end of this lecture, but we'll see. We'll see. So if you manage this in the next lecture, you will more or less have the worst parts of C++. You saw the worst parts of C++, and you will be able to manage successfully, I guess. If you don't understand something directly and immediately, so please don't be frustrated. I mean, understanding the more difficult parts of C++, it just takes time, and take your time, practice a lot, read a lot, ask questions in the forum if you don't understand something which I explain here, so that we can clarify things. Some mechanisms you see today might appear complicated or complex to you. I mean, that's probably the price that you have to pay for the power that C++ gives you over your programs, over the machine. Gives you lots and lots of flexibility, and lots of features. Over time, you will hopefully see that all those mechanisms are really cleverly designed once you get the hang of it. Hopefully that's the outcome for you. So, and maybe just a quick reminder of what are the steps of learning new things. It's not only for programming, but probably can be applied to other domains as well. So at first, yeah, this is awesome. Cool that we have such features in C++. It's excellent. Great to use them. But then if you really need to apply it for yourself, might appear somewhat tricky to you. So maybe not that awesome, not that easy. Maybe frustration sets in. So this is crap. Yeah, I am crap, and I can assure you that you are not crap. So even if sometimes you have the feeling that's not true, you just have to continue on learning about the new stuff, and eventually it might turn out to be okay. And once you got the full understanding of a certain topic, of a certain feature, maybe of C++ even, at the very end it will appear awesome again as it appeared in the first place. And once you get the hang of it, it's completely usable, and you have the full power of C++ and overall its features. So let's start with unions, union type. Union is actually a keyword that you can use in C and C++. And unions can be used to store information. Surprise, surprise. Types can be used for storing information, so that's no surprise, I guess. So but unions are somewhat special because they can store information that share the same memory, or are, in other terms, are alternatives to each other. And the size of your union type, if you declare a variable of some union type that you defined yourself, this variable has the size of its largest data member. We will have an example on how that looks and how that works in a second. And if you have a variable of such a union type, only one member of that union type can be used at a certain time. And it's considered somewhat dangerous because you yourself have to know which member of that union is currently valid and which you are allowed to access. It's somewhat similar, I mean, because unions already existed in C, so C++ just had to adapt them to be compatible to C. And also, of course, C++ had to take the C-style arrays in the language to be compatible. And the C-style arrays had a similar problem because the arrays themselves didn't know their size. I mean, once you declare them, you better keep track of the size yourself. And I mean, a similar issue here we have with union, because you better keep the information what variant, what alternative of a union is currently valid to be used. And unions are particularly interesting if your amount of memory is limited. So if you have to implement and program embedded controllers and similar applications where memory is limited. So how do unions work? So you could go ahead and use the union keyword, union, as you see here. Then you give it a name. The name that I've chosen is CID. And then you have, so to say, a pair of curly braces. And this is very important because people, especially beginners, tend to forget if you define a user-defined type in C++. After your type definition, you have to do a semicolon. Otherwise, the compiler will complain. And maybe the error message is not that clear all the time. So be aware that you have to put a semicolon after a type definition. So, and here we define a union type by the name of CID. And the union type now has three members: a character C, so a variable C of type character, a variable I of type integer, and a variable D of type double. So first of all, first question to you: what would be the size of CID? And I said it on the last slide. I mean, a union has the size of its largest data member, which would be 8 bytes, because on most modern machines a double is 8 bytes. And I mean, a character is defined in C++ to be 1 byte. And an integer on modern machines is usually 4 bytes, so the 8 bytes of that double would be the largest data member. And that means that variables of that type, of that union type, would be 8 bytes in size. If you're curious, you can use the size of keyword to check what is the size of that type, of that data type. That can, of course, be used. I myself never used a single union. Maybe you work in a domain where you have to use unions a lot. Might be later on. So I mean, anyways, you have to know how it works. So how can a union be used? How you can use a union is as follows. Maybe let's have a small example on the right-hand side here. So we can declare a variable x of type of that union type, CID. And now we can access the those are called members here, the individual members we can now access using the point or the dot operator. So for instance, we can access the character here, and we can just write something like x.c to access the character member here, c. And then we can write a character into that thing, because I mean c is of type character, so that should work. And of course then we can also read that character out again. And you can also do it with an integer. So you're using integer now here, or you interpret that piece of data x, you interpret it as an integer right now, right here. So you take that integer literal 100 and store it to the integer I member of that CID union type. And then you can read it again, and you can do the same thing for double. So basically you can use a union type to store data of a certain type in variables of your union type. But be aware that only one alternative holds at a certain point in your program. So what you should not do is, because that's just plain rubbish, so your program would not function correctly if you do that. So please don't write to the integer member I and then use the character variant, the character alternative, because that doesn't make sense, because you just use the integer alternative, and here you wrote to the integer alternative, and here you're trying to use the trying to read the character alternative. That's just plain rubbish. That doesn't work. So only one alternative can be used at a time in order to achieve a meaningful task. Okay. This is C. C is somewhat dangerous, error-prone if you don't implement it correctly, if you are not fully concentrated. So a more modern way and a more C++y way would be to use a stud variant instead. So when you can afford it, just use the C++ type stud variant. It's data type which is defined in the STL, and you can just include the corresponding header file called variant. And variant is in principle just a union type again, so you can have different alternatives, and you can have variables of your variants that you define. And then you can also use one alternative at a time, but also stud variant stores what alternative is currently valid. So you can always check, hey, what's the current alternative that is in use. And you cannot confuse between the different alternatives. So please prefer stud variant if possible. So next, that was union. So next, let's talk about enumerations. So an enum can be used to enumerate something. So why is that useful? Because it allows you to model something which is able to store a bunch of states, really. For instance, if you maybe implement a piece of software and you model some machine state, and maybe your machine is on or off, might be the case that you need to model such a thing. So you could use enums for that, to model these two states on and off. Or a different scenario, maybe if you need to implement a traffic light controller in C++ or also in C. I mean, a traffic light has usually 3 states, so green, yellow, and red. And so now the question is how to encode that in C and C++. And again, you can use enumerations for that. And you use enumerations because you wish to store those different states in an understandable, in a human understandable manner. That's the main goal. So here's an example maybe. So that would be the very naive example how you could do it. I mean, imagine you have a machine and this machine can be in one of two states, so on or off. You can, of course, use a bool, a variable of type bool for that, and true means on and false means off, for instance. You could do it that way. But what if there are many states? Yeah, if there are many states, you could probably use an integer and have a current variable named current state of type integer, and maybe you store the state 21 in that variable. And yeah, but the problem now here is what does the state 21 means? What does it mean, the state 21? You don't know. So what you would need to do is a code comment, and then your colleague who uses your code does not read the code comment, and he wonders what machine state 21 means, or current state 21 means. So that's not at all meaningful and not at all readable. So you better use enumerations for that kind of stuff. And how that works is you use again the enum keyword. It's a keyword. You give your enumeration a name, so to say a type name, an enum type name, which you call machine state. And then again, you have a pair of curly braces, open curly brace, then your definition, closing curly brace, and then you have, again, don't forget the semicolon here. And within your enum definition, so to say, you can just declare a bunch of states that this enum should have. So you could enumerate all your states, and here for the machine state maybe we have two states, on and off, and I mean it's clearly readable. So you can have arbitrary symbols as state names, so to say. And here if you have a machine state variable, it's clear, it's either on or off, and you don't have to misuse other types for that to enumerate states. So for instance, you could go ahead and define a variable ms of type machine state, which you just defined in the above, and you set its state to on, and that's clearly meaningful to any reader of that code. You can also use off, of course. You can also switch the states and assign off to a certain variable of the type. And it's meaningful and it's efficient, and it makes the code much more readable. And I mean, of course, it's sufficient. The compiler under the hood internally stores all your states as integers. But you don't have to do the mapping yourself. The compiler will do it for you and will maintain such a mapping for you. So you can just take the meaningful names, and the compiler under the hood uses fast and efficient integer types. But you do not have to be concerned with that. Exactly. So, and the compiler the compiler starts enumerating at 0 unless you tell otherwise. So if you define an enum such as a machine state in the above, on would correspond to the integer 0 and off would correspond to the integer 1. That is how it works. And you can also use the symbols and print them, and then what will be printed is the mapped integer that the compiler maps for you. So on would lead to a 0 printed here in the first statement, and if you try to print off, it actually prints a 1. So a traffic light might look something like that. So enum traffic light, then all the states that the traffic light can have, so green, yellow, red, and then you end your enum type definition with a semicolon. So if you wish, sometimes that's useful. I mean, there are rare cases where that is useful, but that's why I tell you that. You can also ask your compiler to use a different enumeration. meaning, I just told you that the compiler starts your enumerations at 0. You can also tell it like, yeah, green should actually be 42 as an internal integer, and then it just continues incrementing that stuff. So yellow would be 43 and red would be 44. Yeah. It's also possible to use to define the complete mapping yourself. So you can also say, yeah, green, I would like to use 100, integer value 100 for, yellow 12, and red 4. You don't really need to do that. I mean, most of the time the default mapping starting at 0 is completely fine. So please stick to the default unless you really have good reason to do otherwise. So great thing. So enum, you can't do too much. You can't misuse it pretty much. But there's one catch. So plain old enumerations, which again stem from C, have one problem, and the problem is called namespace pollution. So maybe let's write a piece of code which clarifies what namespace pollution is. So let's include vector, and let's also, and yeah, some of you already mentioned that, you should not really use this thing here. So using namespace std, you should always usually prefix with the corresponding namespaces to avoid namespace pollution. But for our course, we have usually, our programs are usually so simple that we can just use everything from namespace std. But I mean, this example is constructed to show the catch here. So what we can do now is we can introduce an enum which is called type, and we give it two states, a vector and other, and then we just end the definition here. And then in our main function we declare a vector of integer, a variable named v, and we say, yeah, it should have 10 integers. The vector should store 10 integers. And here is the error message that you are getting if you're using GCC. And the problem now is here that the reference to the symbol vector is now ambiguous, because vector exists in the vector include file, of course. I mean, the name of the type is vector, but vector could also be one of the states of the enum types. Right, and so the compiler is now confused here, and it does not know what you're trying to. I mean, the compiler can't make a decision for you, and if the compiler is unsure about something, it usually aborts with an error message. And so the compiler can't really tell, yeah, which vector to be used. Do you mean the vector from the STL implementation, std vector type, or do you mean this state vector here? And that's namespace pollution. If you wouldn't use this directive here using namespace std, and you would prefix here this vector with std std : vector, then compiler would be perfectly fine, because it can now distinguish that kind of stuff. But I mean, this is called namespace pollution here. But besides getting rid of the using namespace std directives, there's also another solution. You can probably use a more safe enums. And if I recall correctly, in C++11, in the C++11 stand, those enum classes, aka scoped enums, have been introduced, which provide type safety. Because the enums, the states of the enums, are only visible in a certain scope, which you always have to be explicit about. And therefore it provides type safety, which is usually what you wish, because the type system is used to prevent you from making errors. And here is an example. So instead of the plain old C enum type, you now use in C++11 and above, you use enum class. So you can define an enum by using enum class. Then you give the enum a name, the type a name, types in this case. You again specify, enumerate all the states, vector and other, and then the compiler is happy even though you are using namespace std directive here, because whenever you wish to access a state of that enumeration, you have to prefix it now with the type's name. So types : vector, this in particular refers to this state here, vector, which you defined in that enum. So you avoid namespace pollution and have type safety. There's one small problem. Sometimes it's relevant to you, sometimes it isn't, or oftentimes it isn't. Because due to the type safety property of those scoped enums, there is no implicit conversion to int anymore. Pardon. So that means you cannot just print a variable of your enum class type to the command line. So this piece of code would not work anymore. It wouldn't just print 0, it would just abort with an error message telling you, hey, the left shift operator is not defined for your enum class, really. If you ever wish to access the underlying integer of an enum class, you have to write the following piece of code in C++. So it looks scary. You just have to believe me at this point. We will learn later on how and why that really works. But using this line of code, you can get the underlying integer of that enum class variable of name type. If you're using C++ 14, the C++ 14 standard and above, you can be a bit shorter and just express it in this line of code. This also gives you the underlying integer. It looks scary, but I mean, that's just the way it is. It's C++. Always using the most archaic syntax. So that would be it, first of all, on unions, for which you probably wish to use stud variant, and enums, for which you probably wish to use enum classes. And now let's come to a bit more useful user-defined types. Useful in the sense that those types which we are going to learn about now are really used to store data and to manipulate data in a meaningful way. And for such user-defined types, you would use the keyword struct or class. So maybe let's have a look at structs first, and then we will learn about the differences between structs and classes, if any. So let's see. If you use you can use this keyword struct to define your own data type. And now on the following slides, we will do so. We will define a simple data type which stores a bunch of data and which can also do some meaningful things to those pieces of data. So let's craft ourselves a simple example. Let's use a struct to define some data type that is able to store some information about a person. How could you do that? So how you could do that is you use, of course, the keyword struct to introduce a new type. You give that type a name. Here in this case, we just name the type person. And then again, pair of curly braces, and at the very end, do not forget the semicolon. And within this struct here, which we are defining right here, we can now list a bunch of variables that we wish to have that data type stored. So this data type person consists of two strings, one string to store the name, another string to store the surname, and an unsigned integer to store the age of a person. And here we're making use of the type system by using the unsigned integer and not integer, because a person usually does not have a negative, is not of negative age, usually. So let's have unsigned to say, yeah, it must be at least positive or 0. So maybe let's have a few facts on structs and variables inside structs. So a variable inside a struct is also called a data member. So name, surname, and age would be all data members of that type person. Besides the term data member, you can also use the term member, in short, a member variable. or fields. Sometimes the data members of a type also are referred to as fields. You can also, and we are going to have a look at that on the next slides, you can also have and define functions inside of a struct. So you can not only store some variables here in that type definition, but you can also have some functions inside of a struct type. And this is then called a member function or a function member. Member function or function member. And data or functions, so everything which is basically stored or defined in such a structure, can be accessed with the point or dot operator. So let's have a small example on how one could use that type. So you could now go on, create a variable Peter by the type person, which you just defined in the above. And then you can access the individual data members, name, surname, and age, and you can assign some data to them. So you can take the string literal Peter and store it in Peter's name, variable name. Or you can also set the surname and set it to Griffin. You can also access the variable age of type unsigned integer and store the integer literal 41 inside of that variable. And after you set the data, you can also again read from that variables. So you can now also ask for Peter's age and print it to the command line, and this expression here would actually evaluate to 42 because it would look up the Peter variable and it would look up the value of the variable age stored in that Peter variable, which is apparently 41 because in the line above we just we just have written 41 in that variable. All right, so that's basically how it works. But this is somewhat tedious because you have to create a variable Peter of type person here, which you just defined, and then you have to set every single individual data member and give it some value, some meaningful value. This is tedious, of course. And also, if you imagine you have some larger data types which comprise more data members, a user of that type might also forget to initialize one of the data members, and then you run into problems because maybe later on you process that data and you access a member variable which is not correctly initialized, and that's usually not what you want. So the question now is there a cleverer way to do that? And the answer is, of course, yes, there is. And how do you do it? You use so-called constructors. So constructor is used to construct a variable of a user-defined type. So let's have an example. So is there a more clever way to get data into a variable of type person? And the answer is yes. Again, now relax, take a deep breath. Person already contains special member functions that you cannot see. And the constructor is a special member function, I have to tell you. So, and if you do not define the special member functions that are required yourself, then the compiler will try to generate those special member functions for you if it needs them. And it will also complain if it can't produce and auto-generate those special member functions. And here our type is essentially perfectly fine, but this here only works really because we're using built-in data types, which unsigned is one of, and STL data types, namely std string here. So that's why it works. So what are special member functions? I mean, constructor is one of those special member functions, but there are some more special member functions. So the special member functions are constructors, which are used when which is automatically executed when you create a variable of a certain type, of a certain user-defined type. And there might also be more than one constructor. So there might be more than one way to construct a variable of a certain type. That will be quite handy if you provide a range of ways to how to initialize data. We will see why that is later on. One more special member function is called the destructor. So, and it's basically the anti-constructor, because the destructor is automatically executed when an object is no longer in use. Meaning, if you have a variable of a certain type and the variable goes out of scope at some point, maybe you process or reach the end of your function definition, then all stack variables automatically go out of scope, and then the destructors of a variable is called. Then you have a copy constructor, which you need in order to perform copies of a type. So if you have a variable of a type, you can also create a copy of that variable. And why do you need that? Please remember that we discussed last time about parameter parsing. So if you pass a parameter to a function, by default, the parameters are copied into that function. And you can really make user-defined data types to behave exactly like built-in data types. That's why the compiler needs to know how to perform a copy of a variable of a data type, which you tell it basically by just implementing the copy constructor. So copy constructor lets you perform a copy of a variable of a certain type. Also, there is in C++ 11, there is a new special member function which is called the move constructor. And the move constructor is used when you need to move an object. So copying is really performing a copy, but sometimes you don't need a copy. Sometimes it's more efficient to just move around a piece of data without copying it. For instance, remember I told you about returning data from a function. And I told you that you should return by value, because the compiler can use return value optimization and all that good stuff. And if you return a piece of data, a variable of a user-defined type, it tries to use its move constructor to make it more efficient, to get that, it tries to move that data out of that function more efficiently than performing a copy, which might be expensive, as we learned last time. Also, you have a copy assignment operator, which allows you to create copies using the assignment operator here. And the pendant to the move constructor, we also have a move assignment operator, which allows you to to move variables of a certain type using the assignment operator. All right, so it currently looks more like that picture here. So quite a bunch of nasty member functions, and you do not have a clear understanding at this point probably how they work, how they have to be used, and why you should also bother with all that madness. So on the next few slides, we're going through all the individual special member functions, try to make sense of them, and at the latest point in the next lecture, it will become clear to you why those might be of use. So why does it have to be so complicated? Maybe let's ask the question. Yeah, it's a valid question. The goal ultimately is to make user-defined types feel like the built-in types. And for that reason, we need those special member functions, because, again, I already told you that the default parameter parsing mechanism is copying. If you call a function and give it an argument, it's copied into that function. So that's why we need a copy constructor. So the compiler needs to know how to perform a copy of your user-defined data type. And same holds for move and all that other good stuff. So, and it will hopefully become clear in time. Also, please be aware that C++ uses a concept called RAII, which is a funny acronym for resource acquisition, is initialization. So when a variable of a user-defined type is introduced, C++ will ensure that a concrete instance of the type will be created. So it will organize memory to be used to store the data required to hold the information of the type. And it also will correctly initialize it. And that's why we need all that madness, really. So let's go through all of these special member functions. Let's write a constructor. How do we write a constructor? This is an example here. So we have a struct person and we still have our data members, string name, string surname, unsigned age. And now this thing here, which looks similar to a function, this is called a constructor. So a constructor is basically a function without any return value. So it doesn't return anything. It does not even return void. So no return type here. And the constructor's name always has to be the name of the struct. So if you wish to have a constructor of a person, that thing must be spelled person. And then a constructor may have a parameter list. Here we have in parentheses, we have a parameter list. And we are basically telling the compiler, yeah, this person has a constructor person. And it takes 3 arguments, 2 strings and 1 unsigned integer. And after the parameter list in parentheses, we now have a constructor initializer list, which you introduce with the single colon. So a colon. And what you then do is you then initialize the data members with the parameters that the constructor receives. So that means please, here, this one maybe as an example, this one basically means take the parameter n of type string and use it to initialize the variable, the data member, the member variable name. And whatever is the first argument, please shove it into name. Whatever string is the second argument, please shove it in that member variable surname. Please use the third parameter, which is of type unsigned integer, and use it to initialize the unsigned integer of that type. So the constructor parameter list here, introduced with that colon, is used usually to initialize all the data members. And then in addition you can have, or you always need, some parentheses. Sorry, those are curly braces, so need to distinguish, need to be precise. So then in addition you can have a body, similar to a functions body. You can have a pair of parentheses in which you are allowed to write some arbitrary code, some arbitrary statements. Here, and in this case what we are doing is we are just printing ctor to the command line, such that we can recognize at which point the constructor will be called or is called, to make it more visible, because it's not very visible sometimes when a certain special member function is being called. Whew, okay, that was tough. Also, because we now defined a constructor which takes 2 string arguments and 1 unsigned integer argument, the following code fails now. So if you write that piece of code here, that the statement is basically an introduction of a variable. So you introduce a variable called Peter of type person, and this now fails because the compiler will tell you, hey, there is no such constructor. There only exists one constructor, and that one constructor that exists, namely this one here I'm just pointing to, takes 2 strings and an integer. And this would call the default constructor, which receives no arguments. And I mean, there is no constructor which receives no arguments. So this code fails now. And a variable of type person can now only be created by using the constructor, which we just defined. So what would work is having a variable Peter and then specifying 2 string arguments and an integer, unsigned integer argument. And this calls here, if you declare a variable Peter this way of type person, then the constructor would be called and it would initialize all the data members of that variable Peter, and it will also execute what's in the constructor's body. That's the meaning here. And yeah, that's exactly what we wanted. We wanted to have a way to obtain resources, so acquire memory, and also to initialize a variable of the type correctly, providing basically no room for any mistakes. So you cannot really miss to correctly initialize a variable of that type person by now. So yeah, so users of the type person cannot fail to initialize variables of that type correctly. And this is exactly what we wanted. So yeah, constructors seem to be quite useful for that job. And yeah, I can tell you they have been designed especially for that job, and that's why it works, of course. So let's talk about destructors. Writing a destructor. So if you wish to write a destructor, you again use the same name. The second here, this line is basically the destructor definition. If you wish to write a destructor, you again have to use the same name as the struct's name. The destructor always has an empty parameter list, and the destructor has this tilde symbol right in front of it, and this should remind you of the logical not. So it's basically not a constructor, it's basically the so-called anti-constructor or destructor. So and this should be the meaning of that tilde. So not a constructor, meaning it's the anti-constructor, the destructor. And we just have it printing detour to the command line. So again, we can associate a piece of code with the destructor that is executed whenever a destructor is being called. And we have that piece of code here just printing detour to the command line. Already told you that. Exactly, great, okay. So, and what's the reason behind having destructor? So users of that type person now can't fail, if the destructor is implemented in a suitable way, they cannot fail to clean up the data and clean up the resources. Let's have maybe a small example. Maybe let's have an example where you define a type which is used to communicate with a database. That might be useful for some applications. So you define yourself a database type which establishes a connection to the database you wish to speak with in the constructor. And then you could implement the destructor to close the database connection. And whenever you have such a variable of some database type, then once it goes out of scope, its destructor is of course automatically called. And then in the destructor, you have the code to automatically close the database connection, meaning that you can never ever forget to close the database connection. Yeah, that's the reasoning behind having destructors, so you can do some cleanup work and you can never forget to do the cleanup because it will be called automatically. All right, so one more example. Let's just assume this program here. So we create a variable Peter of type person, we give it 2 strings and an unsigned integer. So this calls the constructor, and now the member variables, data members of variable Peter are correctly initialized. Here you can now perform some computations and use the variable Peter. You can maybe read out his age or name or surname or whatnot. Can do some computations. And at the very end of main, this Peter variable goes out of scope and its destructor will be called automatically as it goes out of scope, and we finish the computation in the main function right before you return 0 to the operating system. And so another view on things is that constructors and destructors act as a universal do and undo mechanism. which is really an awesome feature of C++. So it's really a great thing. And it's also deterministic. Yeah, so it's a deterministic order in which constructors and destructors are being called. So you can reason about your programs. Java, for instance, does not have that. Copy constructor. How to write a copy constructor? Again, we need to be able to copy variables of a type, of a certain type. For instance, if we pass them into a function, parameter passing. Again, here we have our data members untouched. We also have our constructor, destructor left as is. And this would be the copy constructor. So again, copy constructor, same name as the struct's name, as the type name. And a copy constructor always receives a single argument of type person, of type, of the type that is just to be defined. So a const reference to that type. And in our case, because we're only using STL variables and built-in variables here, we can set it to default. So you can also have special member functions, and rather than providing a definition in parentheses, as you see here for the destructor, or also as you see here for the constructor, you can also say, hey, I wish to have the compiler, I wish the compiler generated that code. So the compiler should generate that piece of code, should generate the copy constructor. So I set it to default. So you can set special member functions to default in such simple examples. And then the compiler will create a copy constructor for you, which just performs a member-wise copy. So when you try to create a copy of a variable of type person, then each data members are copied one-to-one, and a one-to-one copy is performed, basically. So again, same name as a struct, and it receives one argument as shown on the left-hand side. Yeah, already told you that. Here in this case, we can set it to default because we are only using STL types and built-in types, and the compiler knows how to perform copies of those types. So we can just set it to default. However, that will change next lecture, next time, when you have to use dynamic memory allocation and you need to handle dynamic memory on your own. You cannot just set it to default, because then it will produce a wrong result, or it will produce some behavior that you do not desire. So we need to define a custom copy constructor in the next lecture when we are dealing with dynamic memory allocation. For now, it's okay if we just default those things. And if you have set that copy constructor to default, Peter can now be copied. So what can we do? Let's have a look at this code example here. So we can create a variable Peter of type person, initialize it with the constructor, and its CTOR would be called the constructor. Then we can create a new variable clone, also of type person, and we can give it the Peter variable now. And this essentially calls the copy constructor. So here at this line, the copy constructor is called, and clone is now an exact clone of Peter. It has the same data as Peter, as its member data. And also if we call a function which receives a variable of type person as a value, so not a reference, not a pointer, but as a value, as you can see here, then also the copy constructor would be called, and is called essentially. Then you can do some stuff, of course, and at the very end of the main function, the destructor for Peter and clone variable is called. And of course, we at the point of some function, at the end of some function, which we have called here in between, the destructor for the variable P would be called when this function here returns. All right. So in addition to the copy constructor, we also have a copy assignment operator, which you can use to perform copies using the assignment operator. That, I mean, as the name suggests. So how do you do that? This is basically how a copy assignment operator looks like. So a copy assignment operator here, you specify operator assignment. Yeah, I mean, that's what it is. And as an input argument, it receives the exact parameter as the copy constructor. And as a result, it returns a reference to a person type. And you can also set it to default, and it will work perfectly fine for our small example, again, because we are only using STL data types and built-in data types such as unsigned integer. So yeah, again, also this will change once we deal with dynamic memory allocation, but we will do that next lecture. So you can now copy a variable by using the assignment operator. Again, and what's the reasoning? I mean, we already have a copy constructor. Why do we need a copy assignment operator? And the idea clearly is that we wish to be able to define our own data types that behave exactly like the built-in data types. That's the reasoning behind that. So what we can now do is we can construct two variables, Peter and Chris, of type person. Initialize them using their constructors, initializing them with some data. And then at some point in the program, we might wish to use the assignment operator, and we assign the variable Peter to Chris. And here we essentially wish to perform a copy. We wish to copy all of Peter's data into the Chris variable, such that Chris' name is now Peter's name, Chris's surname is now Peter's surname, and Chris's age is now Peter's age. That's the idea. And then, of course, we can do some other stuff, and eventually at the very end, the destructors for the Peter and Chris variables are being called. Yes. Okay, two more to go. So move constructor. Writing a move constructor. We already had this stuff here. So what's new is this thingy here, the move constructor, which has been introduced in C++11. Again, constructor, special member function, so it has the same name as the type's name, so person, and it takes exactly one argument of type R value reference to a person. Oh dear. We will learn what that means, what that is later on, I guess. Again, C++, most archaic syntax. We already have those ampersands, and also when using pointers, the asterisk operator and symbol. Yeah, maybe let's throw some more of those weird symbols in. And so what the move constructor here receives as a parameter is basically a person ref p, which essentially means a temporary value of type person. Oh dear. And we can also, of course, set it to default again, because we're only using STL strings and built-in data types unsigned integer. Yeah, it receives a so-called R value reference, and basically you could think of an R value reference as a temporary variable, or as a variable is the wrong term here. So you can think of an R value reference as a temporary value that has no address. Yeah. Let's have an analogon in a more simple case here. Let's have a variable age of type unsigned integer. Then 42 is an integer literal. So you can think of 42 as a temporary value which has no address, because 42 is just a temporary value. It has no address itself whatsoever. You just have that integer value here and assign it to a variable. And this is basically pretty much what that move constructor thingy here means. So you can give a move constructor some some input, some parameter, which is a value and has no address itself. Hope that helps a bit understanding. I mean, we will get used to it, and we will get the exact understanding what the move constructor does again in the next lecture. Yeah, and this again only works because of STL and built-in data types here. Compiler knows how to move such types itself, so string and built-in data types, and can create a move constructor for itself. So we can just set to default. A person can now be move constructed. So what does that mean? So let's have an example. So we can now have a person Peter, construct a person Peter using its constructor, give it two strings and an unsigned integer. And then we can move that variable Peter to another variable of that same type, namely person here. So please be aware that std move, std : move, is a special function, or is function which is defined in the STL, which can be used to move one variable to another place. So at this point, what that means basically is take the variable Peter and move its contents over into the Chris variable. So this is not a copy. We take Peter's data, the variable stored in Peter's data, and move it into the Chris variable. And also it's very important. I just saw a car accident here outside. Okay, great. I'm sorry. So after you moved some data, the variable where you moved from, namely Peter, is not so you are not allowed to use that after you moved away from it, because the data does not exist anymore. So after you moved the variable Peter into the variable Chris, you cannot, or you are not, you can, but you are not allowed to access the Peter variable at this point anymore. Otherwise, it would lead to undefined behavior. So welcome to the undefined behavior world. Please don't do it. But you can, of course, use the variable Chris now here. And another place where the move constructor is called, so whenever you return from a function by value, so you have a person P within that some function definition, which is constructed, and then you return P. And you could, of course, just create a copy of P, which, again, as discussed in last lecture, might be very expensive if your data type stores a gazillion bytes. Then it might be very expensive. But it's moved at this point. So you just move the data from the variable P and store it in the variable guy, which you initialize here with the return value of some function. So again, at this point, the move constructor is called. And at the very end of the main function, all the destructors are called for Peter, Chris, and Guy. That's how it works. So a person can now be moved. We basically steal the underlying data stored in the type. And sometimes move can be replace a copy. I already mentioned that example, for instance, when you return a value from a function. This will also be very important and relevant once we deal with dynamic memory allocation in the next lecture. And the move constructor is much, how can I put it? It has oftentimes less overhead than calling copy constructor. Sometimes it does not even have any overhead. If the compiler is smart enough to perform some optimizations, then you get a move pretty much for free, almost for free. And you also have a move assignment version of that using the assignment operator as shown here. This one basically is the move assignment operator, which you can also in our case just set to default. Yes. Let's have an example how we can use the move assignment operator. How does it all work? So we create two variables, Peter and Chris, using their constructors, fill in some data, and now we have two variables of the type person. And we can now go on and move the data and steal Peter's data and shove it over into the Chris variable here. And we moved now from Peter's data. That also means after this statement here, after we moved from Peter, we can't use Peter anymore at this point, because if you would use it, it would lead to undefined behavior. So please don't. And then, of course, we can print Chris to the variable to the output stream, and yeah, we would actually then see that Peter Griffin 41 is printed because we moved from Peter here. All right. So that was basically user-defined types with struct. So any other comments? Maybe first comment, do I really have to bother with all those special member functions for such a simple struct type containing 2 strings and an unsigned integer? And the answer is clearly no. And you also saw it that we just could use a default and set all or most of the special member functions to default. We just started with, again, the simple type definition. And also please note that the compiler can generate all the special member functions for plain old data types and for types that only use plain old data types or STL types automatically. A plain old data type is a struct or class that only contains built-in data types. That might also be of importance. You sometimes hear the term pod type, plain old data type, a type that only contains built-in data types like int double character. And, yeah, here we have also 2 STL variables, 2 STL types, namely std string, and also the compiler knows how they have to be copied. Why? I mean, I just tell you, yeah, the compiler knows how they are copied. Why does the compiler know how those variables or those types are copied? Because in the STL, the string type, I mean, it's defined in the STL, and also the string type defines a copy constructor. And so by the copy constructor, the compiler knows how to copy those types. And if you do not provide an own copy constructor, the compiler will generate a member-wise copy of a variable of that type. Hope that makes somewhat sense to you. Yeah, but all those special member functions will become important with dynamic memory, which we will discuss next time. So my recommendation to you, make your wish for compiler-generated constructors and assignments, and I mean essentially the special member functions, make your wish for that explicit. So if you do that and set it explicitly to default, then you will get an error message if the compiler can't do that, which is usually a good thing. And also if your colleagues read your code, they have a better understanding of what's going on if they have it explicitly written there. Finally, person would something like this. So it would have the data members, and it would have a constructor, it would have a destructor, and all the copy assignment, move assignment operators, and these constructors set to default. And that's more or less the final version of person. All right. By the way, one comment. You maybe wonder, hey, we are initializing this unsigned integer age by using basically a copy constructor for integers here, by using the parentheses. Basically, kind of using the unsigned constructor, which clearly does not exist. But since C++11, you can now also initialize built-in data types like non-built-in data types. So meaning like constructor-like, so to say. What does it mean? So that means that you can, of course, initialize a variable p of type person by using its constructor as defined in this line. And you can also initialize an integer variable I by just using the parentheses rather than an assignment operator here. So and just have it initialized to 42. You can of course also do it for all other built-in data types. So you can introduce a variable d and initialize it with the value 1, 2, 3, 4. Similar to what we do here. I mean, that would be just the copy constructor. Or you can think of it as a copy constructor for unsigned types. Also, that does not really exist, but it behaves like that. Besides setting those special member functions to default, there is also the possibility that you can delete certain special member functions. And you can do that by using the delete keyword. What does it mean? So you can go on and have the copy constructor and set it to delete. That then means that a copy is not allowed. So you are not allowed to make a copy of a variable of that type. And if you try to make a copy, the compiler will complain, and the compiler will throw an error at you, and it will not compile that code because you deleted the copy constructor. You might think, yeah, why is that useful? Isn't it a good thing if I can copy data? Yeah, it is. It certainly is. But at some places, maybe to implement stuff from special domains, it makes sense to disallow performing copies for a certain type. And that's the way to specify it. Sometimes that's really, really useful to encode a certain behavior and to model some aspects of your program. Okay, now we discussed structs. So what about class? I mean, if you hear about object-oriented programming and all that good stuff, yeah, class, it's all about classes. So please, once again, remember structs. Structs can be used to store a bunch of data members. They also have special member functions, and they can also have additional member functions which are not special member functions. And all the members of a struct, data or functions, can be accessed via the point operator. And of course, special member functions are called at special places automatically, so you don't have to call them explicitly. And very important here is that you can, when you use structs, you can, users of a struct data type can use and can access all members from the outside. So all data members, all function members can be accessed for a variable of a type which you defined using the keyword struct. That basically means that everything of a struct type is public, which also sometimes is called data is interface. Here's a small example. If you have a struct vec3, which you use to model, I don't know, a vector from mathematics, R3 vector space, so 3 points in the vector space, xyz. You have 3 double variables xyz, and then you can create a variable v of type vec3, and then you can basically access the individual data members, the individual variables using the point operator, and can set them to some initial values. I mean, of course, it's just here to prove point here. Usually you would use a constructor for that one here to initialize variables of that type, as already mentioned. But here you see everything is public pretty much when you use a struct keyword here. So struct, all members are public by default. You can also make some members private using the keyword wonder private. Usually you don't wish to do that for structs, but it works anyway. So you can have a struct defined vec3, so it has 2 double variables x and y, which are just as is. And then you can have a private section and define an additional double variable z. And then this would work. You are allowed to access x and y, but the compiler would not allow you to write some code like y.z and then you try to store a value in that variable, because the compiler will tell you, hey, oh, and this is a mistake, that should be z here. It would give you an error. Yeah, z is declared private. You are not allowed to access z, the variable z. That's disallowed. So you can disallow that and have some private sections of a type definition. But usually you wouldn't use struct for that. You would probably wish to use classes for that. So you would use classes to allow for separation of data and interface. What does it mean? Let's have two examples. Let's have a struct vec3, and we have all, again, the three member variables x, y, z of type double, and we have a class vec3, and we here use the public specifier. So we say, yeah, this section here that follows next after public colon is all public. And here we have no difference. So this thingy and this thingy here is exactly the same in C++. So there is basically no difference between struct and class besides the default visibility. So default visibility using structs is, as you already observed, is public, and default visibility for a class type is private. But by just having a public section here, you can also, of course, make all the classes members public as well. So there's essentially no difference, and this would lead to the exact same behavior. But here in class, as the class's default visibility is private, we have to use the extra keyword public. So please notice that. What other keywords might exist? I mean, already you saw it, private and public, of course, and whoopsie. Private and public, and also protected. But protected we will discuss later on. Protected will become useful when we really use object-oriented programming, type hierarchies, and all that good stuff. We will discuss that later on. So classes allow for separation of data and interface. So what can we do? We can now have a class, and we can have, the default of class is private, but people tend to also, again, use the private section here, the private keyword, to make it even more explicit and tell people, what comes next here is private, X, Y, and Z. And so what we can now do is we can create a variable of type vec3 named v. And then if you try to access any of its data members, the compiler will complain and say, hey, all those variables, and here this is again a mistake. This should be y, that should be z. They are all declared private. You are not able to access those variables, those pieces of data. And now you might wonder, how useful is that? I mean, we now locked ourselves out. We have a vec3 storing three doubles, one after the other in memory, but we are not allowed to access them, so that's not particularly useful, I guess. But again, we can now really separate data and interface. So let's provide namely some functionalities. So let's have our variables or data, let's have the data private, and let's provide some public functions as well. So we can provide a public constructor, and the public constructor we define to take three double arguments, x, y, z, and we use the arguments from the constructor's parameter list in the constructor's initializer list to fill in the data members here. So the x from the constructor's parameter x is used to initialize the x of the data member x, and the variable v of the parameter list of the constructor y is used to initialize the data member y, and so on and so on. And also, let's give it an additional member function. This is a special member function, a constructor. And the next thing here, the next line, is an ordinary member function. So member function, again, like all functions, it has a name, size, it has a parameter list, which is empty at this point. It has a return type, size t. Again, size t is just the type def for unsigned long or something similar. And we also declare to be a const expression function. And again, of course, this function is also associated with a function's body. And we just return 3 because, I mean, that's the idea. Vec3 contains 3 vector entries, so meaning that the size of that vector is always 3, which is why we return 3 here directly. Yes, and because now we have private and public sections. So we keep our data private and we have a public interface. And now all users of that type can only modify and manipulate this piece of data stored by vec3 through the public interface. And this is of course less error prone because you have a well-defined interface which you can use to manipulate all the data. And you cannot just arbitrarily and randomly change values. You always have the public functionalities available. That's what is meant by allowing separation of data and interface. So usually you keep the data private and then you have some public member functions which are used to modify and perform computations and all that good stuff. Here's a small example of usage of that type. So we can now create a variable v of the type vec3. We can initialize it using its constructor and initialize the values xyz with the variables xyz with the values 1.1, 2.2, 3.3. After we constructed that variable v, we can ask the vector variable for its size. So by calling the member function, which we do using the point or dot operator here, dot v dot size, and it will just return 3. And so the result we write in the another variable, v's size. We store the size of the variable. And by size, I don't mean size memory-wise, but how many entries we have in that vector, right? Okay. All right, so let's add some more useful functionality. Let's provide an even better interface. Maybe let's add some more functions. Let's also provide a default constructor. So a default constructor is a constructor that takes no arguments. And in case someone uses the default constructor, let's initialize all the member variables to 0. All the variables are set to 0 by default, initialized to 0. Let's define another member function, which we call Euclidean length, and it just returns a computation here, as the result of a computation here, which computes the length of a vector in a mathematical sense. I mean, the Euclidean length of a vector is basically the sum of squares, and then you take the square root out of that, and that's the length of a vector in mathematics. And therefore, I mean, we can have a member function which computes the length of that vector for us. And at some point, maybe we also wish to be able to print a variable of type vec3 to the command line by using the shift left operator. So here, this is the first example basically of operator overloading. So we will also have it covered as a separate topic here, how operator overloading works. But this is one of the first examples how you overload basically the shift left operator. How does it work? Using the keyword operator here, you tell basically which operator you wish to overload, and this is the left shift here. It's a binary operator, so on the left-hand side you have an output stream, so auth stream is the type, also defined in the STL. And on the right-hand side you have a const reference to a vector. And then basically you take the output stream, OS variable, and just shove all the individual data members into that output stream. And this shift left operator, where you have an output stream on the left hand side and a simple double on the right hand side, this is already defined, so the compiler knows how that works here. And one more thing, those operators here, overloaded operators, are never member functions. But still you can shove them in the class, in the type definition. You can put it directly in the type definition as you see here. If you do that, you need to add the keyword friend, because non-member functions are usually not allowed to access variables private data, types private data. And the thing here is x, y, and z are private, right? So, and because the shift left operator is usually not a member function, it is usually not allowed to access private data. But if you make it a friend and use the friend keyword, then you say, yeah, okay, this thing is allowed to read private data directly. Just a quick introduction, a brief introduction. We will learn all the details on operator overloading in the next lectures. There's a separate topic on that. Yeah, and then our type looks something like that. I just formatted the code in a different way such that we can have some other code here. So let's use the vector type. Let's create a variable v of type vector, and let's initialize it using the constructor. And this means after this line, the constructor has been called, and v's contents xyz are now initialized to 1, 2, 3. Then we can print the variable here, and this calls the shift left operator, which we defined here. So it essentially just shoves all the individual vector components to the output stream. That's essentially what happens here. You can also call the Euclidean length function and compute the length of that vector in mathematical sense and print it, of course. We can also ask the vector for its size, and of course it will give us 3 as an answer here. So struct data is interface class. We always use classes if we need to distinguish between data and interface. And that is the meaning basically. Yeah, and if you use classes, the data can only be manipulated through a public, well-defined interface. And the reasoning for that is, of course, we wish to make the use of a user-defined type very easy, and also we wish to make it safe to use, such that it's hard to introduce errors, right? And but in general, the only really difference between struct and class is the default visibility. So struct's default is public, I already mentioned that, and classes default visibility is private. So I mean, when there's no difference when to use what, and I kind of mentioned it already, I mean at least implicitly, the idea really is please use structs if you have to store some things like plain old data types, very simple types, and use the member functions only as shorthands really, yeah, again for simple data types. For instance, if you need to model a point from mathematics or so, or just, I don't know, some point data type which stores 2 coordinates, there are not many ways how to misuse a simple point containing 2 coordinates. It's probably not much risk. And use classes for non-pod data types, for more sophisticated data types, like if you, as you saw here with the rec3, if you wish to model a vector from mathematics with more complex operations defined on it. Also, if you have some more complex graph types and whatnot, then you would probably always use classes. At least that's convention. All right, that would be it first of all for user-defined data types. We will continue on that next lecture, and you will also already elaborate with user-defined data types in the current exercise sheet, which I already uploaded, I guess. So now maybe let's have a brief overview on how to organize a C++ project in a meaningful way. So how would you do it? I already mentioned it quite a few times, I guess, hopefully. So in C++, C++ allows for separation of code into header and implementation file. So, and I already gave an example in the exercise classes. So please, I mean, it makes sense to attend to the exercise classes, even if you think you know everything. So I give also some details in the exercise classes. Anyhow, so in C++, you can do the following. You can declare a function's header, function signature, to just introduce a function by name and its type. And then you can also define a function. That means you associate a function header with a function body. And those things are two separate, things are separate from each other, can be separated from each other. Unlike programming languages like Java, in Java you only have function definitions. There is no such thing as a function declaration. But in C and C++ there is. And so what you would do is, for logical related code, that is, what is logical related code? That is a collection of functions designed for a specific purpose, or secondly, a user-defined type that may contain member functions and defined by struct or class keyword. And you put all the declarations of the functions and the types, you put all the declarations in a header file, which goes by the ending .h for header file. And a header file always needs some include guards. I will tell you and show you what include guards are on the next slide. So your declarations always in header files, and be aware, do not forget the include guards. And now put the member functions and global variables definitions in an implementation file. So all the definitions of your stuff goes into an implementation file which ends on .cpp. Okay? And so what this allows really is it allows separate compilation of implementation files, also known as modules. And a compiled implementation file or module results in an object file, which ends on .o for object file. So if you have code, you can have multiple files, and usually for logical related code, you have one header file where all the declaration go, and then you have an implementation file where all the implementations go. And each of the implementation files, so .cpp, you can then translate individually, separate from each other. And then you end up with a bunch of object files. And those object files are eventually all linked together by a program which is called the linker. And the linker now takes all your object files and makes links, missing links between those object files, and produces eventually the final executable that you desire. Okay, that's what I just said. So let's have a real example. So maybe let's have some vec3, or vector. Let's have our vector again. And let's have a file called vec3.h, because essentially that's what the major part of that file is. And here in that file, we first of all put a so-called include guard, which is some preprocessor directive. And an include guard looks as follows. So it's for the preprocessor, that's why we start here with the hashtag. So it's a preprocessor directive. So if not def, if not defined the symbol vec3_h_h, then please go ahead and define that symbol vec3_h_. Then you put all your declarations in the file, and at the very end you have an end if again to say, yeah, okay, that's the end of the definition of my vec3 symbol here. Okay. So, and what do we do? Here we have in the vec3, we have the vec3 definition. That means we have the type declaration, not definition, but declaration. So we have the type declaration of vec3. And we have all the data members here declared, and we also have all the member functions declared. But be aware that none of those functions here really has a function body associated with it. So that means that it's only declarations here. And you can also, of course, put free functions. So functions that are not member functions are called free functions, for obvious reasons. You can also have declarations of free functions as well. So here we have a simple free function. You can also have a global variable declared. You say, yeah, I would like to have a global variable by the name of value of type int, and yeah, it should be externally visible. So that all goes in the header file. And then I also have a respective implementation file. So I have a different file called vec3.cpp, and this contains the implementation of all the stuff, the implementation, or also called definition, of all the stuff that I just declared here in the header file. So I include the respective header file in which I declared all that good stuff here. So that's usually what you do. You include your header file of the thing for which you wish to provide the implementation. You also can here now use include IOStream. You can use using namespace standard. I mean, here you can write ordinary code, of course. And you now provide the definitions for all the things that you just declared. So meaning for the free function, you just implement the function. You provide an implementation for that function. And here you see, of course, it's not a very meaningful, useful implementation. It's just essentially the empty function body, but you could put some more useful stuff in that. You can also set the value of the global variable to 42 and initialize that global variable. And then, of course, you now also need to provide implementations for all the member functions. And that's what you do here. You have the member functions, the constructor, the default constructor. You have the constructor that takes 3 double arguments. You have the size member function, the Euclidean length member function, and also the left shift operator overloaded here on output streams. And you associate all of those functions with a function's body here, like in the parentheses. You basically define what this function should do. And also be aware, whenever you define member functions in an implementation file, you have to prefix those member functions, special member functions or plain member function. You always have to prefix the member functions with the type name. So vec3 : vec3 and then empty parameter list would basically be the default constructor. Maybe let's have a different example here. This member function here, this vec3 : size basically denotes this member function size here. Yeah, so you have to say, yeah, you have to basically say, yeah, this is a member function of what type, a member function of what type, and that's why you need to prefix with the type and then : Okay. And now you can have a third file. Maybe you call, I mean, that's usually what you do. I mean, your program always should have a main function at some point, and you put your main function usually in a file called main.cpp. So a user of your program or another colleague of yours, or who knows, whoever has to work on this project directly knows where the main function is defined. So you have at some point a file called main.cpp, which contains the main function. And in the main function, again, you just include what you wish to use. I mean, here you wish to use IOStream, so that's why you include the header file IOStream, right? Because you're using cout. The cout variable is defined in IOStream. You also wish now in the main function, in this file here, you also wish to use free function, and also you wish to use the vec3 type and some of its member functions. And for that reason, you also need to include the corresponding header file, which contains all the declarations of the stuff that you're going to use. So here you include the header file. And again, such an include directive it's just a command for the preprocessor, and it just looks for a file on your machine which has this name, and it just directly copies, it performs a textual copy, it reads all the contents of that file and copies it in that place here. All right, and then what you can do now is, by having your project here split up in 3 files, one header file, 2 implementation files ending on .cpp, you can now compile your project in parallel, separately from each other, because you can now call the compiler to just compile your main your main implementation file here, and you can call the compiler to compile your vec3 implementation file. And then both compiler calls produce object files. So you would have, you would be left with one main.o for main's object file and vec3.o for vec3's object file. And because the compiler includes the respective header files here, the compiler knows how free function works, because it knows here it doesn't return anything and it doesn't receive any parameters. So the compiler is completely happy and can translate your codes by just knowing how the stuff is going to be used by including the respective include files which contain the declarations. So the compiler is happy with the declarations. And at the end you have two object files, main.o and vec3.o. And the thing is now that the object files already contain executable code, but an object file might miss some symbols. Why is that? Because we only know the declaration at this point, we have basically a hole, because if we only compile main.cpp to main.o does not contain the definition of this function. I mean, it contains, so to say, a hole at this point, because the function is not known here, its definition is not known. Same holds for this constructor call and all the other function calls here. We have basically some placeholders. And now the linker comes into place, the linker program, which is also part of your compiler toolchain. So the linker now reads all the object files, and the linker now makes the links between all the object files that have been compiled in separate. So meaning that if you put in the respective object files from those here to the linker will now go ahead and look through your compiled program, and it will see, there's a placeholder free function for which I have to find now the definition. And now the linker looks into all object files, and in this object file, in the vec3 corresponding object file, it will find the definition of free function, and it will make a link between the place where we call it and use it and where it is defined. That's the job of the linker. And the result of the linker command is then the executable program, which has all references resolved. And also, maybe you also make use of some additional third-party library for which you include the header file, then the same game. A library is just a collection of useful functions, which also you get the compiled object file for, more or less. And then you can use all the stuff in the library by including the header, and then you make use of all the functionalities and types that it defines. And eventually you tell the linker, hey linker, please compile all, please make the links to this third-party library. And then the linker will make the respective links. Yeah, it's not that easy, but you will get used to it. It seems complicated, but yeah, in fact it isn't. You just have to get used to that. So again, in brief, each implementation file.cpp file is compiled in separate and is compiled into an object file .o. And once all the sources have been compiled into object files, then the linker will make links between all your object files, and may also add links to external libraries that you are using, and then will produce, as a result, final executable. So, and all that stuff happens here in the language processing system, which I explained to you. So, okay. So here's also a quick overview. So for each source file, for each implementation file, the compiler compiles it into an object file, and eventually the links are made by the linker, which is here. And then you will obtain executable for your target machine. You can also, you can call the Clang or GCC or G++ compiler for all that thing, and the G++ or Clang++ compiler are basically just wrappers or just shells which call the right commands. You can also call the programs individually on your own if you are using a Linux system, or like the virtual machine I provided you with. If you are using the CPP program, you can also just run the preprocessor on its own. So CPP is the C preprocessor, and So C++ is preprocessor. So you can run the preprocessor on your own if you ever need to do that for I don't know, reasons. I don't know. Then you have your actual compiler, which takes the preprocessed source code and compiles it into basically assembly code, first of all. Then you have an assembler program, which takes assembly code and assembles it to the final machine instructions. Then you are left with object files. You can, for instance, once you have an object file, you can use the NM program to list all the symbols that are defined in an object file. Maybe we'll do that later on in the exercise classes. It's quite funny, by the way. Just have a compiler compile source file into an object file, and then you can see what's inside using the NM tool. And you have LD, the linker program, which makes the links as I already described. Usually you do not bother with all the individual programs. Usually you just call a C++ compiler, and the C++ compiler will call all those individual programs for you at all the right places. So, but sometimes it's quite neat if you need to debug some really nasty stuff. Especially linker errors can be quite tricky. So here's a great meme. So C++ programmers buying a monitor that can fit linker errors on one screen. So sometimes you get quite nasty linker errors if you work on larger projects, which make use of libraries and other code and whatnot. So it might be really hard sometimes, and then you really need to use such such tools like NM to really have a look at what's in the object file and what's still missing and where is it located and how do I have to link all that good stuff. One last point for today, so maybe let's elaborate a bit more on compiler toolchains. I mean, as I just told you on the last slide here, compiler toolchains comprise of a bunch of individual programs which are used together to be your whole language processing system, essentially. But there are more tools, especially the Clang LLVM compiler infrastructure. The LLVM C++ toolchain, C++ toolchain, provides additional useful tools, which can be used to automatically improve your code, which is obviously quite handy. Unfortunately, everything in C++ is hard. Usually that's unfortunately true. For instance, even if you just wish to format your code to make it nice and have all the code nicely indented such that it is more readable, even that is hard because you have those preprocessor macros, which we also have as in an individual topic of that lecture. So it's really not that easy, and for that reason you require powerful and cleverly designed tools, clever tools, which not only understand the syntax of your program, but also the semantics. And yes, Clang LLVM is really a great starting point as a compiler infrastructure to build such tools, because Clang LLVM has been designed in a very modular, usable and reusable way. And Clang LLVM, the C++ infrastructure, provides really useful AST-based, so abstract syntax tree-based tools for managing large code bases. And because you have the abstract syntax tree and you can have your tools implement and working on the abstract syntax tree, those programs really know how your code works, and not only know the syntax, but also to some extent the semantics of your program. And really you need such clever tools to write good helper programs, good tooling for that language, because syntax alone is not sufficient for C and C++, unfortunately. So one particular interesting and useful program is called Clang Format. It formats your code. So you give it a file, a source code file, which it should format, and you also give it a configuration file, which basically describes the looks, how you wish to have it all formatted. And then the Clang Format tool will format your source code and make it look all nice. which is really handy. So yeah, if you get it to work, if you get it working, please Clang format your code before you hand it in. It looks really nice after having formatted your code. Also, another very important program is the Clang Tidy program, and Clang Tidy is a tool, also some powerful AST-based tool, which performs some automated analyses and transformations on your source code. And it can, first of all, not only improve your source code, but it can also modernize your source code. Maybe you are left with some pieces of code in your code base which make use of some very old C++98 structures and ways how you wrote code in those times. And the Clang Tidy tool is even able to modernize your code and transform certain language constructs into modern ones that are easier to understand and safer to use. And also Clang Tidy, you run Clang Tidy on your source file that you wish to have tidied up. And also you give it a parameterization via a configuration file where you have all the checks enabled that you wish to enable and all the transformation passes that you wish to have it run on your source code. And of course, there are also many, many more. Please just look it up on the internet. But what I will do is I will, over the weekend, if I find the time, yeah, I will eventually do it. Maybe I have some time over the weekend. I will upload some exemplary configuration files for Clang format and Clang Tidy. And I will have a small paragraph on Panda how to use those tools on the virtual machine that I gave you, such that you are able to make use of Clang format and Clang Tidy. And it will really lead to much nicer looking code. Yeah, that's for sure. And you are very welcome to use those tools because, I mean, if I have to read your source code, and even if other people later on in your life have to read your source code, it's really nice to have it all tidy and formatted in a good way. All right, so I will provide you with some details and detailed descriptions on how to do that. Yeah, I mean, we are completely out of time again, so I will stop at this point here. So, quick recap for today. So, what did we do? We talked about user-defined types. We talked about union types and the uses of union types. We talked about enums, enumerations, and also the C++ 11 variant enum class. We talked about structs and special member functions, classes, and the difference between struct and class. Exactly. So how to organize the C++ project, and at the very end we revisited language processing systems, so in terms of linker and compiler and who's responsible for what, and eventually also we talked about the AST-based, compiler-based tools like Clang format and Clang Tidy, which I will provide some descriptions for you. Right, that would be it for today. So see you in a few hours, I guess, in the exercise classes. Okay, have a nice weekend.